So, yeah, today we will discuss some statistical properties of information theoretic quantities. Okay. So, yeah, I mean, just to reassure you, we have this 1.5 hours, and then there is a tea break, and then we come back again to discuss some problems. So I know, like, listening to me for so long, continuously, yeah, maybe demanding. So I'll try to keep the tutorial short. Yeah, so maybe at 5:30 we will stop. So these are things that are well known to you. X is a Bernoulli random variable, which means it takes the value 1 with probability P and 0 with probability 1 minus P. And X1, X2, Xn are IID with Bernoulli distribution. That means each of them takes the value 1 with probability P and 0 with probability 1 minus P. And S is the sum of n Bernoulli coin tosses. So you all know that the distribution of S is a binomial distribution. N, P, these are the parameters of the binomial distribution. And it has an expectation. S has an expectation. I'm just calling it mu. So what is the expectation of S? The NP, yes. And the variance? NP 1 minus. And we are told that if we maybe take n large, then the probability sort of peaks near about the mean, and then it falls off. Of course, this is a discrete distribution, so I ought to just draw the histogram. So this is what the binomial distribution looks like. So what we'll be interested in today, so this mu is n times p. So what's the probability of this large deviation from the mean? So let us say this point is understand? So you tossed a coin n times, and it was a coin which had the probability of coming head P. But when you looked at your sample of n things, it looks like it is a coin whose probability of being 1 is P plus T. Yeah? And we would like to know how likely is it that a coin whose native probability is P, when sampled, starts looking like a coin. The empirical distribution, yeah, fools us into thinking that it's a coin with a bigger bias, okay? And that those things are typically called this part looks like a tail of some probabilistic beast. Yeah, okay. So we are already taught many things, many inequalities which control the probability of tails. So I would like to review some of those inequalities. And finally, I will try to prove a bound for the tail of the binomial distribution. Now, what I understand is that usually like in most discussions of binomial distribution. Once n becomes large, we say, oh, it is approximated by a Gaussian, and then run to Gaussian and try to get as much out of Gaussian as possible. Okay, but it is approximated by the Gaussian in the limit. Okay, not for finite n. And there is a lot of discussion possible for finite n, and we will engage in one such discussion today. Okay, and it will turn out that for finite n, when n has not become so large that Gaussian kicks in, yeah, the tail probability is controlled by certain information theoretic quantities. Okay, and that is why this is being discussed in this session. So let's take any random variable x. Yeah. So it's a random variable. It takes various values, but it takes only non-negative values. Okay, and it has some probabilities. What I'm saying now is general. It's for continuous or discrete. It doesn't matter. So it has some probability, and it has some mean, mu, and this is a point A. It has some probability. So what are we interested in? We are interested in the probability that x is so now suppose I design a function, yeah, which is 0 here and 1 here. Yeah. So do you agree with this? The probability that x greater than a is the same as the expectation of the indicator function for x greater than or equal to a. What do I mean by indicator function? I don't know if this is the terminology you use. It's a function which is a step function. Yeah, it is 0 up till a and 1 after a. Yeah, so if you take the expectation of this function, yeah, under this distribution, you will just be summing all these probabilities, but that's exactly what we want. Yeah, is this okay? Yeah. Now, this is, always an awkward function to deal with. So what do? We approximate it, okay? And suppose I say that I consider this as my approximation, because somehow integrating this function is easier than integrating this function. Okay. So what is this function as a function of x? So this height is 1. Huh? At a, it takes the value 1. What is this function? What's the equation for this line? Y equals mx plus c, but I want m and c. Yeah, okay, c is 0 because it passes through 0. Yeah, what is m? What is m? What's the slope of this line? Sorry? 1 by a, yeah? So this function is actually x upon e. Good. So, yeah, let me continue. So if I replace this by x upon a, this is a function which is dominating the old function everywhere. Yeah? It is not dominating it on the left of 0. But anyway, I've been told that there is no probability here. Yeah? So I can safely replace this and say that this is less than or equal to the expectation of point-wise, this is dominating this. And this is 1 upon a This A is a constant, it comes out, expectation of X is mu. Sorry, should I write it nicely? Yes. So the probability that a non-negative random variable exceeds A is at most its expectation divided by A. Yes. And you know this has a name, this inequality. You want to play Wordle with me? Yeah. Markov's inequality. It is nothing. It is just this. Okay. Now, of course, yeah, so I'll do one more inequality and then I will go to estimating this. So suppose now you have a random variable and it has a value mu here, and I want to know the probability that x minus mu is greater than or equal to. So that means I'm interested in the tail probability I'm interested in this, the tail probability, where this distance is. What's the probability that the random variable deviates from its mean by A? Yeah. So let's play the same trick. Here there was a step function. What function should I use here to capture this probability? Yeah. So I start the same way. So this is equal to the expectation of the indicator variable for the event that x minus mu is greater than or equal to A. And I want to upper bound this function by a nicer function. Yeah. I mean, step was bad enough, and this is a double step. Yeah. Okay. So what do I do? Well, this is my mu. Then I try to fit a parabola. Yeah. Instead of fitting a straight line, because a straight line will not be able to do. It will kind of go bad here or go bad there. So now I try to fit a parabola. Okay. So I will ask you the same question. So this height is 1, and this distance is A. What is the function? Yeah. So look at this function. At mu, what does this function take? What value does this function take? 0. At mu plus A, 1. So it does pass through this point. Yes. And at mu minus A, also 1. Is everybody okay? Yeah. Yeah. So this inequality is justified because at every point, this parabola dominates this function. And now you see that this is okay. And this has a name. I mean, another Russian. So yeah, I mean, sure you have seen this and you have forgotten this, but yeah. So it's all the same thing. Yeah, we want to sum some probabilities and we try to do it. And if summing it is awkward, we kind of replace it by a summable function. Okay, that is the spirit of many of these inequalities. And now we are going to apply it to the binomial distribution. So we have this binomial distribution, and this is mu, and this is p plus t times n. Let me call it k. This is 0. And this time, see, in my heart, I know that things are falling exponentially. Yeah. So it's okay. I want to suppress these parts, especially by the time I get here, the function should be very small so that I don't capture this probability, because I'm only interested in this probability. So let me try and get a function like this. Yeah. An exponential function of x, which is 1 at k. Yeah. So I write so I choose a value a greater than or equal to 1. Yeah, depending on how steeply I want this exponential function to rise. And I define ax minus k. Now, let us just check. If x is greater than k, greater than or equal to k, what can I say about this? If x is greater than or equal to k, this number will be greater than 1. Yeah, so it will be greater than 1. Yeah, so I fit an exponential function. So x greater than or equal to k, this will be greater than 1. And when x is smaller than k, it will be less than 1. And if I somehow integrate this or sum this, yeah, over the whole distribution, I'm hopefully doing well, because these unwanted terms are being suppressed like anything. Okay, so let me write down the equation. So what do we want? We want summation j greater than or equal to k. What is the probability that the random variable takes the value j? Well, it is n choose j, p to the power j, 1 minus p to the power n minus j. Yeah. This is in fact the probability that the sum is greater than or equal to k. This is exact. Yeah. Sorry, everybody is used to this notation now. Yeah, it used to be NCJ when I was small. Yeah. Okay. So, but I don't want, yeah. So if I now multiply this by a to the power j minus k, then I'm only overestimating it. Because for all values of j greater than k, this quantity is greater than 1. The same principle. Nothing new has happened. Yeah. But the moment I see this form of the equation, I say, oh, actually, now I don't know how to sum this, but let me just bound this by is that okay? I mean, all terms are non-negative, and this was summing from k to n. J equals k to n. Now I'm summing from 0 to n. So obviously, there's no problem. But just, I mean, should I really be scared? Well, this a to the power j minus k is sort of suppressing these terms. So maybe even summing from j equals 0 to n is not so bad, because the unwanted terms are probably going to be killed very badly. Okay. And can you sum this? Is this a summable sort of thing which we used to do when we used to take entrance exams for getting into college? So what is this? No, you don't. So I write it as a to the minus k summation over j equals 0 to n choose j, pa to the power j times 1 minus p to the n minus j. Am I okay? Yeah. And does this look whatever? What's it called? What theorem? Binomial theorem. Yeah. Binomial theorem. Yeah. Okay. Yeah. Okay. So for every choice of A, as long as A is greater than or equal to 1, for every choice of A, this quantity is an upper bound on the tail. Yeah. So now we should try and choose an A so that this quantity is as small as possible, because then it gives us the best upper bound on the tail. Yeah. So you do a calculus, take the derivative, set it to 0, and find the value of A. And if I did it right, so you try to find how small it can be, and when you try to minimize, you will get that A should be this value. Okay, and you can check that this is greater than or equal to 1, because the numerator is always bigger than the denominator in both these fractions. Okay, so let us substitute this value of A into this. Yeah, so with this value of A, if you substitute this, what do you get? P over P plus T to the P plus T. Yeah, 1 minus P. Yeah. So trust me, if you take this value of A, put it in this formula, rearrange, play around, yeah, and recall that K was P plus T times N, then you will get this expression. Okay, yeah, it doesn't look like we are going anywhere, but let me write it as something, yeah. So there is an N. The point is, what is the my logs are to the base 2. Is it clear? I put a minus sign, so this P plus T over P, this exponent P plus T is here, this exponent 1 minus P minus T is here, and this gets reversed under the log. And have you seen this? So here are two distributions. The original distribution of the coin was P 1 minus P. The probability of being 1 was P. The probability of being 0 was 1 minus P. And this is the distribution of a coin which appears to be this biased. Yeah. So this is another distribution. P plus T, 1 minus P minus T. And they have a divergence. And that divergence is this. Yeah. So the divergence between two distributions P and Q. This is my definition of divergence. Okay. Now, this quantity is always greater than or equal to 0, because that was whose inequality? Gibbs inequality. Okay. Yeah. So Gibbs inequality says that this quantity is 0. And sorry, this quantity is greater than or equal to 0. It is 0 only if P is equal to Q. The two distributions are the same. But if the two distributions become different, this quantity rises. Yeah, it becomes more and more positive. And the message here is that if your true distribution, P1 minus P, and the empirical distribution are very different according to their divergence, measuring difference by divergence, then the probability of such a deviation goes down exponentially in n. It goes down, sorry, what did I do? Forgot the n. Yeah, goes down exponentially in n. But the coefficient of n is given by the relative entropy, by the divergence. Okay. So all this was done just to see that at least in this simple case of binomial distribution, a natural calculation leads to the divergence showing up at the rate of decay of large deviations. The rate of decay of large deviations, the rate at which it decays, the coefficient that comes in front of n. Or if you want to do formally, you would take the log of this, divide by n, and take n going to infinity so that all that you get is this. But never mind, we'll just say this is the rate of decay because it is the coefficient of n. And that turns out to be the relative entropy function. Okay. But you will probably get at this point, and then you will have to sum. Yeah. Magic thing. Yeah. So I think, more precise things are known by playing around with this into second order effects if you really want, very precise, better bounds. But for most purposes, this is, so this is the mother of all inequalities, at least for us. Is this okay? Yeah. So no deep message. Only thing is we did a calculation and we saw relative entropy. Okay. So it turns out that this is a general phenomenon, not restricted to binomial distribution. Yeah. This is true for any distribution. And there are two theorems that connect large deviations and relative entropy. Yeah. And I would like to just state the theorem. I don't think it will be very useful to understand their proof, etc. So let me explain. So the first thing is, so the first setting is the following. So So here is a set A. Yeah, maybe it has k elements, A1, A2, A3, AK, yeah, k elements, and P happens to be a distribution on A. Now, you draw n samples from this distribution. You get x1, x2, xn, just as before. Yeah, and then you wonder whether so this is P, and this is some subset. Yeah, let me call it capital Pi of distributions. Now, we would like to know if I draw samples from P. Yeah, I draw samples from P, and then for each element A, I find out its frequency. Yeah. How often did it appear in my sample? So then I get this empirical distribution. What is the probability for large n that when I pick samples from P, they will appear as if the distribution came from pi? Yeah, you understand? So turns out, so let me write down the theorem. So yeah, x1, x2, xn, yeah, samples from P, IID. And P tilde is the empirical distribution of so depending on my outcome, I might get a different P tilde, and that P tilde will fall in this box somewhere. I would like to know what is the probability that this P tilde, yeah, falls here. Okay, it's the same thing. Yeah, I was drawing samples from the binomial distribution, sorry, the Bernoulli distribution, 1, 0. Yeah. And what is the probability that when I take n of them, it appears as if it has something where it has more than, yeah, more than P plus T ones instead of P ones. And Sano's theorem says the following. So I haven't defined this. This pi is a set of distributions. Capital Pi was a set of distributions, and I'm looking at the divergence. I mean, the notation is the divergence between this set of distributions and P, yeah, and the set of the pi between this is so that is among the distributions that are here, yeah, choose the one which is closest, yeah. choose the Q for which this divergence between Q and P is the closest, okay? And then the probability that samples drawn from P will look like they came from some distribution here will go, yeah, so this is a weird way of writing. You should probably read this as 2 to the power minus n times so if you have a set of distributions and you're drawing samples according to this distribution, the probability that that sample will have empirical distribution lying in this set goes down exponentially as n increases, yeah, with n. But the coefficient of that exponent is this. And for which value of Q? The Q star that minimizes this, okay? There are some conditions needed on this pi. I'm not writing them now, but this is the spirit, okay? Questions? Roughly making sense. Yeah, maybe you should compare it with what we did before, yeah? There was a coin toss. So this distribution previously was and this set of distributions was all of those with various values for probabilities for one, where the probability of one was p plus t or more. The probability of one was p plus t or more, yeah? Because if you take a empirical distribution for anything which produces, say, k ones, then the empirical distribution is k over n, 1 minus k over n, okay? So the set pi was all those empirical distributions here. And we were asking, if I'm picking elements according to the distribution P, what are the chances that it will start looking like a distribution from this set? Okay. And that goes as this, and this is a general theorem. Okay. So relative entropy is an important quantity in statistics. So I will tell you one more theorem about relative entropy, and then we will do some properties of relative entropy. But please ask, yeah? Hypothesis testing. So, I mean, this is a fundamental goal, more or less, of statistics, okay? So, I mean, it's like your chemistry lab. You've been given some unknown compound, and you perform some experiment. But the experiment gives you outcomes with some distribution, yeah? And you are somehow told that if it is copper sulfate, then you will get this distribution for the colors, etc. Whereas if it is, I don't know, potassium permanganate, something, yeah, it will give you some other distribution. And you observe for some time. And you know, these distributions are not completely apart. It's not as if in one case you get red smoke and in the other case you get blue smoke, and with one experiment you are done. They have overlaps. So with one sample, you will not be able to tell whether it was this or that with high probability. So what do? You perform the experiment again and again, and then see what is the empirical distribution. Does it look like copper sulfate? Does it look like this data came out of potassium permanganate or something? Okay. So that is the situation. So you have P1 and P2. Yeah. So you've been told that the data is coming. So the alphabet is still the same. Yeah. These are distributions. Both these are distributions on the same set. Yeah. And one of them is P1, the other is P2. And you're told that the data is coming either from P1 or from P2. Okay, and you have to tell which one. Yeah. So you suddenly see a sample and you have to decide whether this came from P1 or from P2, and that is the field of hypothesis testing. Okay. So what would you do? Yeah. So usually in hypothesis testing, there is one of them is called the null hypothesis. Yeah. And this is the alternative hypothesis. Okay. And you would like to design a test so that, so this is, yeah. So you perform the experiment n times and you get a point here. Yeah. If the sample lands here, yeah, then you say that you reject the null hypothesis, and this is called what happened. So if you observe it n times, if it lands here, you're going to say, well, it doesn't look like the null hypothesis holds, something is wrong. Okay, it seems to be coming from here. Okay, but if it falls outside, you sort of accept the null hypothesis. Yeah, there is no reason to reject the null hypothesis. So this is the usual statistical setting. So what does Stein's lemma say? It looks very similar to Sano's theorem, but here we have two things instead of one. So if these two distributions are very similar to each other, yeah, if these two distributions are very similar to each other, then it is clear that it will be much harder to distinguish them. And what does harder mean? That means you will need many more samples to distinguish them. Yeah? And if they are already very far away, yeah, then maybe a few samples will suffice. Now, one understanding of this difficulty of separating this hypothesis from this hypothesis is described here. That is, suppose you have just try to understand what this is saying. So usually in statistics, when they're trying to distinguish between two hypotheses, yeah, what they say is, give me a test so that if the samples are drawn from this, yeah, I should get some constant probability of success, that the sample should fall in the set Bn with constant probability. Yeah. But if a sample comes from here, yeah, then, sorry, sample comes, yeah, sample is being drawn according to P2, then the probability that it falls inside the set Bn should be very, very exponentially small. Yeah. So there's always an asymmetry. You fix a threshold here, let's say 99%, and then you try to design a test so that if this hypothesis holds, then you will not reject it. Yeah, most of the time you will accept it if the hypothesis is true, if P1 is true. But if P1 is false and P2 is true, yeah, then the probability that you are going to say that P1 holds is going to be exponentially small. Okay, so this is the usual statistical hypothesis testings. But what does this Stein's lemma say? It tells you the efficiency with which the probability is going to go down. You see, I mean, it is again written in this way. You should read it as 2 to the power minus n . So suppose they say that if you are in P1, it should be 0.9. But if you are in P2, I want this to be 0.000001. Okay. So how many tests do I need to do so that I have this level of confidence? So you will set this quantity to be equal to whatever level of confidence you want. Okay. And then you will solve for n. But while solving for n, this d will come in the denominator. Yeah. When this d comes in the denominator, that means if this d is small, then you will need lot of samples. Yeah. And if this d is large, that means P1 and P2 are already well separated, then you will need fewer samples. Okay. And this is tight. That is, any test, yeah, sorry, this was only one direction. This says that any test which succeeds here with probability alpha, and no matter what alpha, yeah, even if it succeeds here with constant probability, it will necessarily succeed here also with this probability. Yeah, with this probability. Okay. And there is the converse, that is, if it turns out that P1 and P2 have a good relative entropy, then it is possible to design tests so that, yeah, so let me write it down. So this is a limitation. You cannot do better than this. And this says you can do this well. Okay, so Stein's lemma says the efficiency of hypothesis testing between two distributions P1 and P2, okay, at least for large n, there is this little limit. Yeah. What did I see? Yeah. So for large n, the efficiency of hypothesis testing, the number of samples you need to drive down your error probabilities, is determined exactly by the relative entropy between P1 and P2. Is that okay? Yeah. Questions? Sorry? That's right. This is true for, yeah, but we'll have to define things properly. So there is a whole survey written on information theory and statistics. So I'll put a link to that survey on my notes. But in chapter 1, these are already the two fundamental theorems, Sano's theorem and Stein's lemma. Good. So yeah, in the remaining time, we will move away from statistics now. And I just want to understand relative entropy. Yeah, various properties of relative entropy. Some of them will be just verifying our intuitive feeling for how, when distributions are different, when distributions are similar. But of course, our intuition needs to be verified. We need to check whether the mathematics actually says what our intuition says. So that's what I'm going to do. Now, one reason for spending, it turns out that relative entropy actually is a much better behaved quantity than entropy, mutual information, etc. Yeah. What do I mean by better behaved? It can be defined for quantum systems also. Okay. And many of the intuitions that we develop in classical for relative entropy, yeah, they carry through in quantum. Okay. So, many of you probably already work in quantum information theory. So it's a good idea to understand classical relative entropy well and yeah, try to see if analogous things can be worked out in quantum. Again, there are two surveys written on quantum relative entropy. There was a course given by Witten during COVID, apparently, like a lecture series on quantum information theory. And a good part of those lecture notes talk about quantum relative entropy. And there is an older lecture note, I forget, from the early 2000s, also written by a physicist from England. And that also sort of praises relative entropy. Let's do a little calculation. So suppose P is a and U is the uniform distribution. What is this quantity? Yeah. So let's write down the definition. I mean, I invite you to do it yourself. Let's say the size cardinality of A was n. So I should write yeah. What does this look like? Yeah, what does it look like? Sorry. Yeah. Yeah. So basically, if you take the relative entropy of any distribution P from the uniform distribution, it is actually the deviation of the distribution from the uniform distribution. Because if the distribution was uniform, what would its entropy be? Uniform distribution, its entropy would be log n. And somehow this relative entropy measures how much the distribution has varied. So let's think of so here's a chain rule for relative entropy. So suppose P is the distribution on, there is a random variable x1, x2, sorry, two random variables x1, x2, and their joint distribution is P. And there are two distributions y1, sorry, two random variables y1, y2, and their joint distribution is Q. They both take values over the same alphabet. And so we can write down the relative entropy. And just to emphasize, this is the distribution of x1, x2, and this is the distribution of y1, y2. Yeah. Now, I could look at just x1 and y1. Yeah, just x1 and y1. And they are also random variables, and they are distributed over the same alphabet. So you have a big system, and you are looking at the part of the system. Yeah. So the part of the system is x1 here, and the part of the system is y1 here. And there is a relative entropy between x1 and the distribution of x1 and y1. Okay. And then, so we would like to understand the relationship between the relative entropy of the part and the whole. Okay, so this is the relative entropy of between the two wholes. And we look at the relative entropy between these parts. Now, if you think of D, divergence, as a measure of distinguishability, because all our calculations seem to suggest that if the divergence is high, the distributions are distinguishable. Okay, so suppose somebody is making an observation here which has two columns of data, x1, x2. Okay, and somebody else here who is making two columns of data, y1 and y2, and then they give you these two tables and ask you, are they coming from different distributions? You would do some analysis to do that. Now, if suppose somebody drops the second column, gives you only the first column. Yeah, I mean, intuitively, it seems reasonable that it should be now harder to distinguish the two data. Yeah, so let us see if that comes out from our formulas. Is it clear? A is the set ranges over the possible values for x1. B ranges over the possible values for x2. Y1, Y2, it's the similar. Y1 also has the same range of values as x1. Y2 has the same range of values as x2. So this is what it is. All right. So let us expand summation AB, PAB log PA times, what should I write? PAB, probability that the outcome is AB is the same thing as the probability that the first outcome is A, and the probability that and you know, log is very friendly to multiplication. Yeah. So you get summation over AB, PAB log PA by QA plus summation over AB, PAB log of P, B given A divided by Q. Is that all right? Most of the time only A appears and we are summing over B. So if I sum PAB over B, what do I get? Fix a value of A and sum over B of PAB. Fix a value of A and sum over B PAB. Sorry. Yeah. So I can drop the B here because this part is independent of B and call it PA log PA by QA, which sort of looks like a relative entropy. I'll let you think about what it is. And what could I do here? I say summation over A, PAB, PA, summation over B. I want you to tell me what else I should write. What should I write here? Good, thank you. Yeah. So it's become quite pleasant, yeah? What does it say? The relative entropy of between these two composite systems is the relative entropy between the first part, because this is the relative entropy between, what am I writing? Px1, the marginal distribution of x1, and the marginal distribution of yes. And then this is, we are multiplying PA with some quantity. In this sum, A is fixed. Yeah. So what does this look like? Yeah, but it looks, when you multiply PA with some quantity which depends on A, it looks like an expectation. Yeah, it looks like an expectation over the choices of A of this. And what is this? This is a relative entropy between PBA, the two conditional distributions for this choice of A. Yeah. So this is plus, let me write it for now as sum. I write x1 equals A and y1. Yeah. So we started with the relative entropy of the composite system, and we took away this system, x2, and we got this relative entropy. And to account for the difference, we get this expectation. Okay. What do we know about these quantities? These are always, relative entropy is always greater than or equal to 0. Yeah. So from this we get that the relative entropy of the combined system is always greater than the relative entropy of any of its parts. Because this quantity is always greater than or equal to 0. Okay, by the way, the fact that relative entropy is greater than or equal to 0, I probably did not make one. Maybe I did it earlier. See, that entropy is greater than or equal to 0 is not a surprising thing because it is PA log 1 upon PA. Every term is non-negative and you're adding it up. Here, you have two distributions. One is P, the other is Q. Sometimes Q may have larger probability, sometimes P may have larger probability. Okay, so this ratio can be positive or negative. Sorry, this log of this ratio can be positive or negative. But nevertheless, Gibbs inequality tells us that there are negative terms here, but overall, it will always be non-negative. Okay, yeah. So anyway, so indirectly, we are using Gibbs inequality in this, in proving this, because how do we know that these quantities are greater than or equal to 0? Because of Gibbs inequality. So suppose M is the transition matrix M is a transition matrix of a Markov chain, and P and Q are distributions on the states of M. Yeah. So, yes, so there's a Markov chain, and we start with some distribution P, or we could start it off with some distribution Q. So there is initially relative entropy between P and Q, and so initially P and Q are two distributions on the input states, on the states of the Markov chain, and they had a certain distinguishability, divergence, and that was this. Then we sampled the initial state from P, ran the Markov chain for one step, and we got this distribution on the states of the Markov chain. I mean, sorry, this is the convention I was taught yesterday. That is, probability vectors are column vectors, and you multiply it with the transition matrix, and you get a new column vector that is the probability distribution of the state after one step of the Markov chain. You do the same thing to Q. Yeah? What do you think? Will it become easier to distinguish or harder to distinguish between the two states? Easier? Harder? So suppose, yeah, I mean, it should probably be clear that it perhaps shouldn't be. Suppose the Markov chain was this, yeah, that there was a sink state and everybody just headed to the sink state with probability 1. Yeah. So initially you had some distribution P and another distribution Q. They were distinguishable. One step of the Markov chain, the probability, okay, you have it becomes a delta on this state. Yeah. And then the two distributions become the same. Yeah. So which way should the inequality work if our intuition is correct? That is, running a Markov chain is only going to mix them up, make it harder to distinguish. Do you believe that? Yeah. So then which one should be bigger than which one? Left should be? Yeah, D is distinguishability. Yeah. Okay. And this is a theorem. This is always true. Okay. So let us try to prove it in some way. Yeah. Okay, so I'll erase this. Okay, I'll come to that. Let me just. Yes. No, they can only get closer. Yeah, that's a general fact about any process. Yeah, any randomized process. Well, the question is, what does closer? Closer with respect to what metric? Okay, so we are. Yes, sorry, no, but let me finish. You understand? You're going through the Markov chain. It is mixing things up. Yeah, so it could be that things that were different are now landing up at this. I mean, the distributions are becoming similar. Yeah. Dimension of. Oh, yeah, okay. So for me, Markov chain is an abstract object, not a walk on a spatial system. Yeah, sorry, I don't mean random, but random walks are a special case of Markov chains. So you have a state space, yeah, and in each step, you are in a current state, like what we did in last time on a random walk on a graph, yeah. So yeah, for us, random walk on a graph and Markov chain are indistinguishable objects. So you are at a state. Next time you toss a coin, and that coin tells you where to move. Next time you move. Yeah. So initially you had a certain distribution on the space. Once after one evolution, you can be anywhere. Question? Nothing. M is just a transition matrix. Any transition matrix you apply to the distribution. Yeah, it's nothing. Nothing. In fact, I probably have misled you by saying Markov chain. It can be any stochastic matrix. Yeah. So you were in one of these states and you applied a random transformation. Yes. So suppose this had k possible things and L possible things. So initially you were a distribution on these k things. You evolved it, and now you became a distribution on L things. Okay. So initially you had a distribution P and Q on these k things. You evolved them, and now they have become P prime and Q prime, but on L steps. The point is, if you didn't have distinguishability initially, you are not going to get distinguishability later. Okay, yeah. And if this was the case, what would the transition matrix look like? What will be the dimension of the transition matrix? I mean, what cross what? Sorry? Yeah, so yeah, K cross L or L cross K? Huh? L cross K. Yeah, I just wanted to tease you a little bit. Yeah, okay. Yeah. So it is. Yeah. So yeah, so this is L and this is K. Yeah, and you multiply it with P. So yeah, I mean, unfortunately, matrix multiplication works like this. English language is written like this. What can I do? Yeah, somebody had a question. Yeah. No, unfortunately, it is not a real metric. Yeah. For example, it's not symmetric also. It's not even symmetric. Yeah. It has some properties. In fact, yeah, so if we were focusing on relative entropy, there is a certain, so it satisfies certain properties of Euclidean distance squared. Okay, yeah. So No, distance square doesn't, only distance satisfies triangle inequality. Here, no, so the Pythagorean theorem, yeah, which is true on Euclidean space, is also true for this D, okay? But I'll have to define it correctly. Yes. Yes. So if that's so if P, unfortunately, yeah, so I should have been more careful. Yeah, so if I'm sorry, if it is block diagonal and P happens to be supported here, meaning 1 over K, 1 over K, 1 over K, yeah, and Q was supported somewhere else, yeah, and then when you multiply, you will get some vectors. Now, the final vector could still be the same, even though this. Now, you are saying if it is block diagonal, then you are like this, yeah. The trouble is that if you're thinking of P and Q, where P is like this and Q is like focused on some other block, yeah, the relative entropy here is an annoying number because for all these values of A, PA is 1 over K and Q is 0, and this is infinity, okay? So, yeah, you have, so relative entropy is defined only when if QA is 0, PA should also be 0. Okay, so that 0 log 0 by 0 is considered 0. Okay, but if PA is non-zero and QA is 0, then relative entropy is not a good tool for you to use. Okay, is that okay? Yeah. Good. So what was I saying? Sorry, I've forgotten where I was, but it doesn't matter. Oh, yeah, I'm trying to explain to you why evolution of a system can only reduce the relative entropy. Intuitively, it is clear, yeah? If we say, sorry, I'm just, this is a complete word game. If relative entropy was supposed to capture distinguishability, okay? That means the best possible way you can distinguish these two systems. But among the ways of distinguishing this system, I also have the liberty of applying M. Yeah. Okay. So why can't I say that my experiment included first applying M and then trying to distinguish? Okay. So that is the spirit of the philosophy of all this. But let us see. Yeah. So how do you evolve the system? You are in some state, X, and then, let me call it little s, and then you pick a number you in the range, let's say 0 to 1. And depending on whether the number landed up here, you go here. When the number lands up here, you go here. When the number lands up here, you go here. And so, yeah. So you can think of, okay, so before, this is the evolution, stochastic evolution. So first, let me explain the following thing. So suppose you had two distributions. I'm doing a special case of that. Suppose I have a function f which goes from to some other y. It's a function. And I look at what do you think happens? So x1 and y1 were some two random variables. They had some distributions. And now I applied a function to both of them. What do you think? Do they become more distinguishable, less distinguishable? I mean, this function could, for example, have been the constant function. Yeah. Yes. Is this all right? So we would believe this. Our intuition says that this must be true, because if you have two systems and you perform the same, a common deterministic transformation on them, yeah, it should be the same. Now, okay, so why is this true? Do you believe this? So let me explain what this is. This is a distribution of the random variable x1, and this is the distribution of the random variable y1. Okay. Now I took x1, I sampled x1, and applied the function f and wrote it next to it. So each value of x is tagged with its value f. Y1, I tag it with. Now, the probability distributions are not changing. Yeah. Putting this f1 next to it doesn't change anything. I'll let you think about it. Then this quantity is exactly equal to this. Yeah. Just taking some value and deterministically tagging it is not going to change anything. Yeah, because the value could always have been computed. Yeah, it is not some special extra information. Okay. So anyway, you just write down the formula and check that this will be exactly equal to this. But now we are in business, because in this, if I now keep this part of the system and throw away this. Sorry. It rings only once, right? Yeah. Okay. So we will stop. So just one remark. Basically, yeah. So instead of f of x here, you put z on both sides here, z and z. Then this will be equal to this, and the function can be that deterministic function which takes the state and the coin toss and determines which state S prime you have to go to, and you will get this, and this will look like that multiplying by the transition matrix. Okay. So let me stop here, yeah, for now. So what have we done? We started with a calculation for the binomial distribution, and the relative entropy seemed to pop out, yeah. And then I told you that the fact that relative entropy popped up there was not a coincidence. It is a special case of a general theorem called Sanno's theorem. And Sanno's theorem has a cousin called Stein's inequality, yeah, Stein's lemma, yeah. And Stein's lemma controls the rate at which you can reduce errors in hypothesis testing. Okay. Relative entropy, as somebody was thinking, like seems to have some metric-like properties, but unfortunately it's not symmetric. But there is a lot of geometrical sort of behavior that relative entropy has, and I will put references in the notes. So it is worth studying. Okay. So we'll stop here. We'll meet at what time? At 4:30. How long is the break? Half an hour. So we meet at 4:30, and then we'll continue for 1 hour. So I'll erase the board and put out some problems, and then we'll